we're going to talk about inverse functions today. So first off, a quick little reminder. If you have a relation, it is a function if you don't have your input value go to more than one output value. So you can look at your set of ordered pairs and go, okay, well, if 2 only maps to 3, 3 only maps to 4, and that is a function. Or you can look at your graph and think about the vertical line test. So if you can draw a vertical line through your relation and it only intersects it one time, that means you don't have any points that share the same x value. So it is a function. There are special functions that have the additional property of being one-to-one, where each y value also corresponds to only one x value. So if you look at these up here, the first one has the y value of 3 that gets mapped to by 2 different x values. So that means it is not one-to-one. The second one, you can use the horizontal line test to see that you have 2 points that share the same y value. So that one's also not one-to-one. Now, being one-to-one is important to see if a function has an inverse or not, which we'll discuss later. Right now, if you look at example A, that's another relation that is not one-to-one. On B, you can think about the graph. If you rewrite that, it's a parabola, which means that you do have 2 points that share the same y values. Or if you think about plugging in a couple of different x values, say you plug in 1 and you plug in -1. In either of those cases, you're going to get an output value of +1. So for those 2 input values, they share the same output value, which means it is not one-to-one. On C, I would think about the graph. That's a linear function, so it's going to pass the horizontal line test and be one-to-one. It's important to be able to identify functions that are one-to-one because those functions have inverses. So inverse operations are operations that they undo each other when they're performed one after another. Say you have these 2 functions. If you start with the input value of 2 and add 3 to it, and then take that result and plug it back into g of x and subtract 3 from it, I end up back where I started with my original value of 2. So an inverse function with notation looks like f to the -1 power, but it means inverse, not 1 over that function, is the function that undoes your original function. So to find an inverse of a function, one way you can do it is swap your x and y values because that is switching your input and your output. So if I look at this set of ordered pairs, first decide if it's one-to-one. If it's not, then it won't have an inverse. This one is one-to-one, and that means my inverse of this function f is going to be the set of ordered pairs where my input and my output, or my x and y coordinates, are swapped. So just this set of ordered pairs right here. If you look at B, this function is an equation instead of a set of ordered pairs. If you think about the graph of that one, a cubic, it is going to be one-to-one. So I can find my inverse. So to find f inverse, I'm going to use just y notation-wise. And then I'm going to swap my input and my output, or my variables that represent them. And then I always like to have my equations solved for my output variable, y. So I'm going to take the cube root of both sides, which is going to give me y plus 1 equals cube root x, and then subtract 1. So you'll end up with y equals cube root of x minus 1, or notation-wise, f inverse of x equals cube root of x minus 1. On part C, if you think about that function, it's again a quadratic, which means it is not one-to-one, so we'll be unable to find an inverse function for this. Let's look at a situation where you've got this function that takes in degrees Celsius and gives you out degrees Fahrenheit. We want to find the inverse of this function, which is basically going to swap those and take in our degrees Fahrenheit and give you out the degrees Celsius. So what I'm going to do is I'm going to write my original equation with just y equals 9/5 c plus 32. And then I am going to swap my values that represent my input and my output. So I'm going to swap c and y. and then solve for y, since that represents my output. So I'll subtract 32, and then I'll multiply both sides by 5/9, and end up with y equals 5/9 times c minus 32. Now it doesn't really make sense to leave my variable as c in that, since really my input now stands for degrees Fahrenheit, so I'm going to change the letter so it's less confusing. And I'll go ahead and call this function g of f. What if you want to check and see if two functions are inverses? Well, if they're inverses, if you perform both of them, one following the other, in both directions, and you get your original input back. So we're going to do some function composition. First, I'm going to do f of g of x. So I'm going to take my function g of x and plug it into f, replacing my variable. So I'll have 4 times the quantity 1/4 x minus 1/2, which is going to give you just x minus 2, and then plus your 2 gets you back to your original input of x. We need to check both directions. So if you turn it around and say I'm starting with f of x and then performing g of x, I'll take and plug f of x into g of x and have 1/4 times the quantity 4x plus 2 minus 1/2, which is going to give me x plus 1/2 minus 1/2 equals x. So in both cases, I get my original input value, x, back, so they are inverses. You might say, well, why don't I just start with f of x, swap x and y, and show me that it gets me the equation for g of x? You could do that, but it would really only be halfway. You'd also have to start with g, swap x and y, and show you that it gets you back to f. Let's look at a couple of graphs of functions. If we take a look at a couple of graphs and want to know if f of x and g of x are inverses, you could consider some of the coordinates of your points. So you have 2, 5, and 5, 2. You have 1, 2, and 2, 1, and you have 1, 0, and 0, 1. So it would appear, at least for those listed points, that the x and y values are swapped and that they're inverses. Now graphically, we actually know that two functions are inverses if they're reflected across the line y equals x. So if for every ordered pair the x and y values are swapped, then they're inverses, which is true if they're reflections across the line y equals x. So these two are inverses.